Okay, there, AP Chem scholars. We are bearing down on the end of Unit 4. Here we are in Section 8, which is about acids and bases. Okay, we talked a little bit about it in one of the previous sections, so really not totally new, just kind of expanding on it a bit. You should know already that we're talking about double replacement reactions in general when we're looking at these ionic reactions with the acids. Okay, we've talked about the Arrhenius system already, and so we know that we expect an acid to be something that's going to give a hydrogen, a base that's something that's going to give a hydroxide, and because we have hydrogen and hydroxide, that means that water is always going to be a product, and in theory, a salt would be made from the remaining cation and anion. Nothing new there. Okay, we what we do have to talk about though that is different when we do double replacement with acid bases is that, first of all, we assume that an acid and a base are aqueous to begin with, that they do dissolve in water. But that does not mean that they're going to dissociate. Okay, only strong acids and strong bases will dissociate. The strength of an acid or base is determined by its ability to dissociate in water. The more hydrogen ions released, the stronger the acid is. The more hydroxide ions released, the stronger the base is. Okay, so it's all about dissociation. So really, in a way, a strong acid is something that has weak bonds so that the hydrogens come off easier. That's something we'll circle back to way later in the year. A strong base is a strong electrolyte. That's why we call it a strong acid. Okay, it's excellent at conducting electricity. Same thing with a strong base. A weak acid is a weak electrolyte. A weak base is a weak electrolyte. No, nothing surprising there. But remember, only strong acids and bases are assumed to dissociate completely. So if it's a weak acid or weak base, for now, we're going to assume that it doesn't dissociate. Yes, it really does dissociate a little bit, and that's something for when we get into equilibrium. There are 7 strong acids you are supposed to know, listed in red there. There are 8 strong bases you are supposed to know, listed in blue there. Okay, I don't need to belabor the point. Obviously, the bases are easier to figure out from looking at a periodic table because we have the alkaline metals and then the bottom of the alkaline earth metals. And yes, technically francium and radium would fit into this if we were including radioactive elements, but we're not. Okay, it's the acids that will take a little bit of getting used to remember. All right, so let's look at some simple acid-base reactions. In the first scenario, we're going to take a strong acid and a weak base. So we're going to take nitric acid, magnesium hydroxide, and of course we know that acid plus base is going to give water and salt. So our acid is HNO3, our base is MgOH2. The H's and the OH's come together and make water. Now since there's 2 OH's and 2 H's, we should have 2 waters. And the salt then would be the cation and anion left over, so magnesium nitrate. And that really should be aqueous. I can. Let me do it. All right. Oh, you'll have to deal with that for now. We know that nitric acid is a strong acid, so it does dissociate. We know that magnesium hydroxide is a weak base. It does not dissociate. And magnesium nitrate is a soluble salt. It does dissociate. So this would be the complete ionic equation. And then, of course, we have to eliminate our spectator ions, which are the 2 nitrate ions. And so we're left with 2 hydrogens plus magnesium hydroxide makes 2 waters plus magnesium ions. So that is our net ionic equation. All right, so now let's take a different scenario. Let's reverse it and go weak acid, strong base. So we're going to take acetic acid as our weak acid, calcium hydroxide as our strong base. Now acetic acid as a weak acid will not dissociate. Calcium hydroxide as a strong base will dissociate. Water, of course, is liquid. It's not going to dissociate. And calcium acetate, the salt that's produced, is soluble. Acetates are usually soluble, so we do dissociate it. And so now this time the calcium ion is the spectator ion. And so when we take that out, we're left with 2 acetic acid plus 2 hydroxide yields 2 waters plus 2 acetate ions, right? No. Okay, because we always balance empirically, so 2 to 2 to 2 to 2 should be 1 to 1 to 1 to 1. Okay, so that is the correct net ionic equation. All right, what about if it's strong and strong? All right, so now we'll take nitric acid and calcium hydroxide, the acid and base from the previous two questions. Okay, so we know that they're strong, so we know they're going to dissociate. So nitric acid is going to give us hydrogen nitrates. Calcium hydroxide is going to give us calcium and hydroxides. And then the product, calcium nitrate, would dissociate. It's a soluble salt, so we get calcium and nitrate. So now we see that we have two spectator ions, the calcium and the nitrate. So that would leave us with this. But again, we always simplify. We balance empirically. Okay, so it's 1 to 1 to 1. Hydrogen plus hydroxide yields water. All right, what if it's a weak acid and a weak base? Well, then neither are going to dissociate. So let's take the acetic acid and magnesium hydroxide from those first two examples, put them together. Okay, the products would be water and magnesium acetate. Okay, magnesium acetate is still a soluble salt, but there are no spectator ions. So the complete ionic and the net ionic happen to be the same thing. That's fine. It can happen that way. Okay. So please keep in mind that does not mean no reaction. There is a reaction, okay? It would mean no reaction if everything canceled out in a double replacement. And clearly, that's not the case here. Everything is not aqueous. Not everything is canceling out, okay? It will never be no reaction in an acid-base reaction. Okay. So there are two special reactions that we have to talk about that are acid and base-ish, okay? Reactions with sulfides, when an acid is mixed with a salt containing a sulfide ion, the product is going to be H2S gas, okay? And that has really nasty rotten egg smell. You probably did a lab in the past where that was produced, and so you're kind of familiar with it, okay? So for example, if I took HCl and sodium sulfide, okay, the product would be hydrogen sulfide and sodium chloride. Why are we talking about this? Well, you know that sulfur and oxygen are in the same family, so obviously we're seeing a little bit of a similarity here in terms of the fact that water and this sulfide is, an acid plus this sulfide is making H2S instead of H2O and a salt, sodium chloride. So there are parallels there, okay? So in the net ionic, okay, the sodium and chloride are both spectator ions. So I'm left with two hydrogens plus sulfide, making H2S. And then another example is with carbonates or bicarbonate. Okay, this is another gas-producing reaction that you're expected to know. So when we have an acid mixed with a carbonate or bicarbonate, the product that we would expect to make is carbonic acid, except carbonic acid is not very stable and it decomposes immediately, so we don't even consider it really ever forming, okay? So if you look at the formula for H2CO3, there's, if I pull out an H2 and one O, I'd be left with CO2. So you see it's a one-to-one decomposition there. So for example, if I take hydriodic acid and mix it with baking soda, sodium bicarbonate, okay, what I would get is, that doesn't seem right. Yeah, that's not balanced, right? Yeah, I like that better. Okay, anyway, I digress. So what we have is this acid, and let's pretend for the moment that this is our base. We're getting water and we're getting a salt, but we also get that carbon dioxide thrown in here, okay? So the net ionic would have hydrogen plus the bicarbonate ion making water and carbon dioxide, okay? So those are special reactions you got to be aware of, especially this one. The carbonate-bicarbonate one comes up frequently. Okay. So in those last two examples, the sulfide and the bicarbonate, we were talking about them as salts, but at the same point, we're kind of talking about as if they were bases. And that's where the Arrhenius definition kind of breaks down. Okay, when we think of the Arrhenius definition, we tend to think of substances that have OH ions in it. But really the definition is that produces OH when it's mixed with water. Okay, so we're going to clarify why that is as we go into the Bronsted-Lowry system. Okay, they defined an acid as any substance that can donate a proton, which is just a hydrogen ion. After all, hydrogen should have one proton, one electron. If we take the electron away, all that's left is a proton. So they talk about acids in terms of protons, and they use the terms like monoprotic, meaning it has one hydrogen, diprotic, it has two hydrogens, etc., etc. Okay. That should be accept. Okay. So a base then is any substance that can accept a proton or hydrogen ion. So now bases become anything that can accept a hydrogen ion. So compounds that have non-bonding pairs of electrons very often can accept hydrogen. So all of a sudden it expands immensely, and any anion negatively charged is going to attract a cation. So you could see then why the sulfide ion being a -2 ion, or why the bicarbonate ion being a negative ion would attract hydrogen ions and react with them. So that does make it a base in the Bronsted-Lowry system. Okay. Now there's another major difference in this case. I'm getting ahead of myself. When we talk about an acid-base reaction, in the Arrhenius system we said it makes water and salt, but in the Bronsted-Lowry system, an acid and a base make a new acid and a new base, and because they're products, they're referred to as the conjugate acid and the conjugate base. Okay, so I'll show you an example of that in a minute. And there are some substances then that are able to not only give a hydrogen, but also take a hydrogen, okay? And so they could be an acid or a base, depending on what they're mixed with. We call them amphoteric substances. Water is amphoteric, okay? Because it has hydrogens, it could give a hydrogen off, but the oxygen has non-bonding pairs of electrons on it that could attract hydrogens to it, so it can be either or. Okay, so let's look at this acid-base reaction. Okay, HF plus S2 negative yields HS minus plus F minus. All right, we see that HF has a hydrogen, so obviously it's giving a hydrogen because it ends up as F minus. We see that S, being negative, is able to attract a hydrogen ion, which it obviously does in order to become HS negative. Okay, so in our reaction, HF is the acid, but the sulfide ion is the base. Now, think about this. If you looked at HF before, you would have called it an acid anyway. So we're not really totally revamping our definition of acid, but with base, now we are, because we would have thought of that as just an anion or whatever else. It doesn't have OHs in it. We wouldn't think of it as a base. Okay, so now if we look at the reaction from right to left, okay, HS has a hydrogen, F doesn't. So obviously HS would be an acid in terms of the reverse reaction. So that's why we would call it the conjugate acid. And that means that F would have to be the conjugate base, taking on the hydrogen in order to go from right to left. Okay, so when we talk about conjugates, it's just that they're on the opposite side. Okay, when you look at them, we talk about conjugate pairs. Okay, HF and F are conjugate pairs. There's only one hydrogen difference between them. Okay, that's what makes a conjugate pair. Okay, so the acid always becomes a conjugate base. Conversely, the base always becomes a conjugate acid. Again, sulfide and HS minus, the bisulfide ion, okay, there's only one hydrogen difference between them. They are a conjugate pair, okay? But conjugate pairs always go opposites of each other. So if it's an acid, its conjugate would be the base, okay? If it's a base, its conjugate would be the acid, okay? So with that in mind, if I'm talking about OH as a base, what is the conjugate acid? Okay, I'm not going to say the answer yet. And if we're talking about H2SO3 as an acid, what would its conjugate base be? All right, so think about that because the answer is coming up now. Okay. So if OH is a base, its conjugate acid is going to be water. And if H2SO3 is an acid, its conjugate base is HSO3 minus. Again, there's only one hydrogen difference, and it's just an issue of if it was an acid, then we're taking a hydrogen off. If it's a base, we're adding a hydrogen on. Okay, so that's all that we're talking about in these processes. So now you notice it says monoprotic reactions here. I kind of skip over that. Every single reaction in the Bronsted-Lowry system is always monoprotic. There's always one hydrogen being transferred. If there is more than one hydrogen, it comes off in steps. And that's what the second reaction is showing. So the first step says, all right, if we take H2SO3 and mix it with hydroxide, I can get HSO3 minus in water. But that HSO3 and water, the HSO3 could give another hydrogen off to become a sulfide ion and turn the water into something called hydronium, H3O+. Okay? The hydronium ion is something that will be important down the line. But again, right now, not a big deal. Just need to know that it does exist. Okay? So I want you to take a minute and try these 4 reactions. See if you can figure out what the products would be for these. So you need to figure out which one is the acid, because the acid is going to be giving the hydrogen. The base is going to be accepting that hydrogen. All right? Pause it if you need to. Let me finish this out. All right, so H2O and F. Obviously, H2O is the acid in this situation because it has hydrogen. Fluoride doesn't. So it's going to give a hydrogen, make hydrofluoric acid, and the hydroxide ion. So notice that the hydroxide ion is being produced in the reaction. That really is the essence of the Arrhenius definition, that hydroxide is produced. Okay? It doesn't necessarily have to be in the compound. Where's it being produced from? From the water. Remember, it's aqueous reaction, so sometimes chemicals just react with the water right there. All right. What about in this case? Well, this doesn't have hydrogens. This does. So obviously, this is my acid. It's going to give a hydrogen. So I'm going to have HPO3, 2 negative now. It was 1 negative, but I took away a positive charge. It becomes more negative. And now this gains a hydrogen, so it becomes a hydroxide ion. What if I mix hydroxide ion and hydrocyanic acid? Well, all right. Now, both of them could give off a hydrogen, but this one's negatively charged, right? This is neutral. So it would make more sense that this chemical that we would call hydrocyanic acid is the acid. And we know, again, not totally eliminating what we learned before, hydroxide ions usually indicate bases. Okay? So if it's a base, it's going to take on a hydrogen. That's going to make it water. The HCl that's got to give off the hydrogen becomes CN negative. Now the fourth example, that is really tricky, as it says up top there. Okay, we have 2 negative ions. How do you know which way it goes? Okay, well, to be honest, if you picked either of these answers right now, that's fine. Okay, as long as you decided one of them had to give a hydrogen and went with it. It would come down to the strength of the acids, and that's something that comes up in a subsequent unit, so I don't know why they bring it up here, but, you know, I mentioned it anyway. But in case you really want to know, the second reaction actually is the correct one. H2S happens to be a little bit stronger acid. HS minus is a stronger acid than HPO4, so it's the one that's going to give the hydrogen in this situation. All right, so that is acids and bases. And if you have questions, let me know. Go bang out that AP assignment. Talk to you soon, guys. Bye.